Formula Formulae Set number 202 of the chapter Gravitation. Formulae Set 02 of the chapter Gravitation. Number 1. Relation between gravitational field intensity. Relation between gravitational field intensity and the gravitational potential. I equal minus dv by dx or dv by dr. Gravitational field intensity I is equal to the negative value of potential gradient. In diagram, capital M is the mass of a given body or raised body. And we consider another body or test body of mass small m prime, and that will be moved from one point to another point. M prime is equal to 1, that is the mass of the test body is unity or unit. Test body will be moved from the point A to B. Gravitational field intensity, that means gravitational force of attraction experienced by the test body of mass m prime equal 1 is I, which acts towards the given body of mass capital M, and displacement of the test body from the point A to B is dr. Potential at the point A is Va equal V, and potential at the point B is V minus dV. Potential at the point is smaller than the potential at the point A, which is closer to the given body of mass capital M. Hence, we can say that the gravitational field intensity I is the gravitational field intensity I is negative the negative value of gravitational potential gradient. Gravitational potential gradient, that means dv by dr is the potential gradient. Change in potential with respect to distance. dv is equal to minus I dr. dv is the difference in potential between the point A and B, or change in gravitational potential when one moves from A to B. Therefore, V equal integration dV. Therefore, V equal minus I dr. V equal minus I dr. Similarly, gravitational force of attraction Fg equal minus du by dr, where u is the gravitational potential energy. This is the gravitational force of attraction in terms of gravitational potential energy. Gravitational force of attraction, where u, capital U, is the gravitational potential energy. Gravitational potential energy. Number 2 formula, gravitational mass. Gravitational mass. Small mg is the ratio of gravitational force of attraction Fg and gravitational field intensity I. Fg by I is the gravitational mass, which is which is defined as the magnitude of gravitational force of attraction or gravitational pull Fg experienced by a body per unit experienced by a body in a gravitational field of unit gravitational field intensity. So gravitational mass is the gravitational pulled in a gravitational field of unit gravitational field intensity, gravitational mass, which is defined as the magnitude of gravitational pull experienced by a body in a gravitational field of unit gravitational field intensity. But inertial mass mi equal force divided by area, force divided by acceleration, which is the inertial mass. Here small a is the acceleration. Gravitational mass of a body is affected by the presence of other bodies near it. The gravitational mass of a body is affected by the presence of other bodies near it. But the inertial mass, gravitational mass is mg equal fg by I, and the inertial mass mi equal f by a. Force divided by acceleration. Inertial mass of a body remains unaffected by the presence of other bodies near it. That is the main difference between the gravitational mass and inertial mass. The gravitational mass is measured by a spring balance, whereas inertial mass is measured by inertial balance. Number 3. Satellite. Number 3. Satellite. So this is a planet or Earth, and this is the distance of a point at altitude h. O is the center of Earth. Capital M is the mass of Earth. Capital R is the radius of Earth. A is a point on Earth's surface, and we consider a smaller body of mass M, which is actually a satellite. Satellite of mass M is at the point B at altitude h. The satellite is at altitude h above Earth's surface. The satellite revolves around Earth with a tangential or orbital velocity v0. v0 is the orbital velocity along the tangent bt1, and the satellite revolves around Earth in this circular orbit of radius r plus h. And this is the circular orbit along which the satellite of mass m revolves around Earth. Number 1 quantity, orbital velocity, v0 is equal to root over gm by small r, where small r is equal r plus h, which is the radius of circular orbit of the satellite. Capital R is the radius of the planet or radius of Earth. H equal altitude of Earth. v0 is the orbital velocity of the satellite. Therefore, v0 equal root over g capital M divided by r plus h, where capital G is the gravitational constant and capital M is the mass of Earth. v0 has another expression. Now, at the point A on Earth's surface, small g is acceleration due to gravity, and Fc equal Fg, that means centripetal force, is supplied by the gravitational force of attraction, and orbital velocity has another expression v0 equal r root over g divided by r plus h in terms of small g or acceleration due to gravity. So this is the orbital velocity of a satellite revolving around Earth, orbital velocity of a satellite of mass small m, orbiting at altitude h, around Earth or around a planet of mass capital M. Number two, physical quantity in connection with the motion of satellite around Earth is time period of revolution of satellite. Time period t is equal 2 pi small r divided by v naught equal 2 pi under bracket r plus h divided by v naught. V naught is our orbital velocity. We get the expression of time period as 2 pi by r root over r plus h whole cube divided by small g. Capital T equal 2 pi by r root over r plus h whole cube divided by small g. That is the time period of revolution of a satellite around Earth. And also we can replace the value of small g 2 pi by r root over r plus h whole cube dot r square by gm, since acceleration due to gravity, that is small g equal gm by r square, equal 2 pi root over r plus h whole cube gm. Therefore, t proportional 1 by root m, that means time period of revolution of a satellite, is inversely proportional to square root of mass of planet or Earth, where capital M is the mass of Earth or planet. Again, t is equal to 2 pi by r root over r plus h whole cube 4 by 3 pi rho gr, putting the expression of acceleration due to gravity on Earth's surface. So finally we get 3 pi r plus h whole cube divided by rho gr cube. Therefore, time period is proportional to 1 by root rho. Time period of revolution of satellite is inversely proportional to square root of density of planet or Earth. T equal root over 3 pi r plus h whole cube divided by rho g r cube. When the satellite is very close to Earth's surface, in that case h is much less than r, means altitude is much less than radius of Earth or planet. In this case, the expression of orbital velocity v0 will be r root over g by r plus h. Now neglecting h with respect to r, we get r or v0 equal Therefore, V naught equal approximately equal root over gr, since h much less than r, and we can assume h is equal to 0 with respect to r. V naught equal root over gr, as g equal 9.8 meter per second square, which is the acceleration due to gravity on Earth's surface, and r equal 6.4 into 10 to the power 6 meter, which is the radius of Earth. In that case, orbital velocity of a satellite very close to Earth's surface will be V naught equal 7.92 kilometer per second. So this is a satellite at the point B, and we can draw the Earth. This is Earth of mass capital M, who is the center, and capital R is the radius of Earth. H is the altitude of the satellite if H much less than R. In that case, V naught equal root over gr. The satellite at the point B will be very close to Earth's surface. In that case, very close to Earth's surface. In that case, H much less than R, and V naught will be 7.92 km per second. Also, time period of revolution is t equal to pi by r root over r plus h whole cube divided by small g if h much less than r. In that case, t equal 2 pi root over r by g. That is the expression of time period of revolution of a satellite which is very close to Earth's surface. T equal 2 pi root over r by g. As r equals 6.4 into 10 to the power 6 meter, which is the radius of Earth, and small g equal 9.8 meter per second square, then t will be 84.6 minutes. 84.6 minutes. That is the value of time period of revolution of a satellite very close to Earth's surface. Number 3 formula: height of satellite. Height of satellite, or what is the expression of a altitude of satellite. Now time period of revolution is 2 pi by r root over r plus h whole cube divided by small g. Therefore h equal bracket open t square r square small g divided by 4 pi square to the power 1/3 minus capital R. That is the expression of altitude or height above which satellite revolves around Earth. H equal t square r square g divided by 4 pi square whole to the power 1/3 minus capital R. That is the altitude or height. The satellite is at the point B at altitude h. The expression of this altitude h is t square r square g divided by 4 pi square whole to the power 1/3 minus r. Now number 4, physical quantity is angular momentum of a satellite. Angular momentum L is the product of r and p, where p is the linear momentum, r is the radius of circular orbit, which is r plus h, and linear momentum p equal mv naught. So L equal r plus h mv naught. O is the center of Earth, and this is Earth, and B is a point at altitude h. Small m is the mass of satellite. Satellite has orbital velocity v naught along this tangent, and linear momentum p acts along the same tangent. H is the altitude of satellite above Earth's surface. Small m is the mass of satellite, capital M is the mass of Earth. Angular momentum L, that is vector L, acts in this direction. Vector L acts outwards with respect to the plane of circular orbit of satellite, and the expression of L will be root over expression of angular momentum L will be under bracket small m g capital M small m r plus h to the power 1 by 2. L equal number 5, kinetic energy of satellite. Kinetic energy of satellite. Ek equal 1 by 2 small m v naught square, half m v naught square, where v naught equal root over gm by r plus h. Therefore, ek equal g capital M small m divided by 2 r plus h. That is the kinetic energy of satellite. gmm divided by 2 r plus h, which is the kinetic energy of satellite. Number 6, potential energy. Number 6, potential energy of satellite. U equal minus gmm divided by r plus h. That is the potential energy of satellite. U equal minus g capital M small m divided by r plus h, where capital M is the mass of Earth, small m is the mass of satellite. The satellite is at altitude h, and potential energy of this satellite at the point B at altitude h is U equal minus gmm by r plus h. Number 7 formula is total energy of satellite. Total energy of satellite. E equal Ek plus U, sum of kinetic energy and potential energy, Ek plus U. Therefore, E equal minus gmm by 2 r plus h. That is the total energy of satellite. Satellite of mass small m, which is at altitude h above Earth's surface. Capital M is the mass of Earth. Capital R is the radius of Earth. The satellite revolves in the circular orbit with orbital velocity v0 at the point B at altitude h, and kinetic energy of satellite is gmm divided by 2 r plus h. Potential energy is minus, which is negative gmm divided by r plus h, and total energy is minus gmm divided by 2 r plus h. So E equal, that is the total energy of a satellite, which is negative minus gmm divided by 2 r plus h. Now additional knowledge is what kinetic energy K equal mod of E, and kinetic energy Ek equal half of mod of U. Kinetic energy is equal to the magnitude of total energy, and kinetic energy is half the magnitude of potential energy of satellite. Number 8, physical quantities, binding energy of a satellite. Binding energy of a satellite. Binding energy is given by EB. EB equal minus E, which is numerically equal to the negative value of total energy of satellite. EB equal minus E. Satellite at altitude h above Earth's surface. O is the center of Earth. Capital R is the radius of Earth. This is Earth of mass capital M. A satellite of mass small m is altitude h. The satellite revolves in the circular orbit with orbital velocity v0. And if an energy of EB is supplied to the satellite will be removed from its orbit. That is the main concept of binding energy. Satellite will be removed from the circular orbit of satellite. Satellite will be removed from its orbit if this energy, that means binding energy, is supplied to the satellite. Is supplied to the satellite to remove the satellite from its orbit. The satellite from its orbit. Number 4 formula in connection with the chapter Gravitation, geostationary satellite. Geostationary satellite or geosynchronous satellite. The satellite remains stationary with respect to Earth. That's why it is called geostationary satellite or geosynchronous satellite. This is Earth, and this circular orbit or circular line is the equator. So this is the equator or circular line containing diameter of Earth. We can draw another orbit which is coplanar with respect to equator, and this is the orbit of geostationary satellite. And geostationary satellite is at height h, r is the radius of Earth. Here we have the geostationary satellite. This is the geostationary satellite of mass m, small m, and this geostationary satellite revolves around Earth in this orbit, circular orbit with orbital velocity v0, and this is north-south axis of Earth, north-south axis of Earth, which an Earth rotates from west to east with angular velocity omega equals 7.27 into 10 to the power minus 5 radian per second. And this is the geostationary satellite of mass m, which revolves around Earth in this direction with orbital velocity v0. This orbital velocity is along the tangent on this circular orbit. Orbital velocity uh, revolves in the same direction as that of the rotation of Earth, and angular velocity of geostationary satellite acts vertically upwards, and angular velocity of geostationary satellite will be same as the angular velocity of Earth. For geostationary satellite, number one, altitude of geostationary satellite is 36,000 kilometer. Orbital velocity of geostationary satellite is 3.1 kilometer per second, and angular velocity of revolution of geostationary satellite around Earth is 7.27 into 10 to the power minus 5 radian per second, which is the same angular velocity as that of Earth. And we can find the altitude of geostationary satellite using this formula, that is h equal to square r square t divided by 4 pi square to the power 1/3 minus capital R, where capital T equal 24 hours, which is equal to 86,400 seconds. Capital R is the radius of Earth, which is 6.4 into 10 to the power 6 meter, radius of Earth. Number 5, polar satellite. This circular orbit is the equator of Earth. Equator. We can draw another circular orbit, a polar satellite, which is at a right angle to the equator. This is the orbit of polar satellite, which is inclined at an angle 90 degree with the equator, and along this, in this orbit, polar satellite revolves around Earth, and this is the polar satellite of mass small m. Polar orbit. This is the polar orbit which has angle of inclination, which is polar orbit whose angle of inclination with the equator, with equator or equatorial plane of Earth is 90 degree. Polar satellites are used. The polar satellites are used for getting the cloud images, for getting the cloud images, atmospheric data. They are used for getting the cloud images, atmospheric data, and to detect ozone hole in atmosphere. To detect ozone hole in atmosphere. Number 6, escape velocity. Number 6 is escape velocity. So this is Earth. Who is the center of Earth, and R is the radius of Earth. Earth of mass capital M. A body of mass small m is at the point A on Earth's surface, which is thrown vertically upwards, with a velocity ve, which is escape velocity. A body of mass m is thrown vertically upwards with escape velocity ve, and we can draw gravitational field or space around Earth to which gravitational pull is experienced. A point B on the gravitational field. B is a point on gravitational field, and this gravitational field extends up to infinity. And the body which is thrown from Earth's surface with escape velocity will reach the point Q just beyond gravitational field. And at the point Q, the body will be at rest, means final velocity v prime will be 0 at the point Q. This imaginary spherical space is the gravitational field which extends up to infinity gravitational field. An escape velocity from the surface of Earth is given by VE equal root over VE equal root over 2G capital R. VE equal root over 2G R, where G is the acceleration due to gravity on Earth's surface. VE equal root over 2G R, which is escape velocity with which a body of mass m is thrown upwards from Earth's surface in any direction, such that the body just crosses the gravitational field, just crosses the gravitational field, and comes at rest at the point Q, just beyond the gravitational field. A body of mass m is thrown with escape velocity v from Earth's surface, and it will reach the point Q just beyond gravitational field, and at that point the body will be at rest, means v prime equal to 0. Escape velocity has another expression, that is ve equal root over 2g capital M divided by capital R. ve equal, where small m is the mass of the body and capital M is the mass of Earth or planet, where capital M is the mass of Earth. ve equal root over 2gm divided by R. A body of mass small m is thrown upwards with a velocity v greater than escape velocity from Earth's surface, that means from the point A of Earth's surface, and the body will move to the point Q beyond the gravitational field. The body of mass small m will reach to the point Q, will reach to the point P beyond the gravitational field. The body of mass small m will reach the point Q beyond the gravitational field, and the gravitational field extends up to the point B. And the body continues to move at the point P beyond gravitational field with velocity v prime. And v prime is not 0. When a body of mass m is thrown with a velocity v greater than escape velocity ve, when a body of mass small m is thrown with a velocity v greater than the escape velocity ve, it will go beyond gravitational field. It will go beyond gravitational field and it will continue to move with a velocity v prime, such that v prime equal root over v square minus ve square. That is the velocity of the body at the point P beyond gravitational field is v prime equal root over v square minus ve square, provided the body is thrown with a velocity greater than the escape velocity from Earth's surface. Number 2, additional information. Again, a body of mass small m will be thrown from the point A on Earth's surface with a velocity less than the escape velocity. Mass a body of mass small m will be thrown from the point A on Earth's surface of Earth of mass capital M. Small m is the mass of the body, capital M is the mass of Earth. And the body of mass small m is thrown upwards with a velocity v less than escape velocity. And the body will reach to the point and the body will reach to the point the body will reach to the point B. The body of mass m will reach to the point B up to the altitude h within gravitational field, and the point B velocity of the body 0. V prime equal to 0 means the body comes at rest at the highest point B, and the point B is at altitude h, and we can denote now we can denote gravitational field at the point A x equal to r, and the point B is at a distance r plus h from center O of Earth, and the gravitational field extends up to the infinite distance. That means x is equal to infinity at the gravitational field. When a body of mass small m is thrown upwards with a velocity v less than escape velocity v prime, ve from Earth's surface. When a body of mass small m is thrown upwards with a velocity v less than escape velocity from Earth's surface, it will go or it will come at rest at the point B at altitude h, such that half mv square plus under bracket minus gmm by capital R, that is sum of kinetic energy and potential energy at the point A, will be equal to half mv prime square plus under bracket minus gmm by r plus h. From that we can prove that the altitude up to which the body will reach and comes at rest at the point B is 8, and small h will be r v square divided by ve square minus v square. This is the altitude up to which the body of mass m will reach and comes at rest, provided the body of mass m is thrown upwards from Earth's surface with a velocity less than escape velocity. H equal r dot v square divided by ve square minus v square. A body of mass m is thrown with a velocity v less than escape velocity ve, and the body will reach to the point B at altitude h, and h is what r v square divided by v square minus v square, and escape velocity, the value of escape velocity ve equal 11.2 kilometer per second. The value of escape velocity from Earth's surface is ve equal 11.2 kilometer per second. Therefore, ve equal 11.2 kilometer per second. That is the escape velocity from Earth's surface. Escape velocity for any body from Earth's surface VE equal 11.2 kilometer per second. Number 7. Kepler's laws of planetary motion. Laws of planetary motion. Kepler's laws of planetary motion. Kepler's first law, we can draw the elliptical orbit of revolution of a planet, and this is semi-minor axis of elliptical orbit and semi-major axis. And sun exists at one of its foci. Sun of mass m is at the focus f1 and f2 is the another focus, and this is the elliptical orbit of revolution of a planet, and we can draw a planet of mass small m. This is the planet of mass small m. This is the planet which revolves around sun, sun with a velocity, with orbital velocity v0. For every planet, or every planet revolves around sun in an elliptical orbit, and sun is situated at one of its foci, at one focus of the ellipse. Number 2, Kepler's second law. Number 2, Kepler's second law, elliptical orbit of revolution of planet. Sun exists at one of its foci of the elliptical orbit, and a planet of mass m revolves around sun in this direction. This is the distance vector of planet from sun. Vector r is the distance vector of planet from sun. Planet initially was at the point B, and after some time the planet will reach to the point C. The planet reaches to the point C in time t. The planet starts to move from the point B at instant t equal to t second, and it reaches the point C at instant t equal to t plus dt. And dA is the area swept out by the distance vector in time dt. dA by dt is constant, and dA by dt is aerial velocity. Aerial velocity, where dA is the area swept out by the distance of planet from sun in time dt. According to Kepler's second law, aerial velocity of planet around sun is constant. Aerial velocity of planet around sun is constant. dA is the area swept out by the distance vector of planet from sun. Distance vector of planet from sun in time dt, in time interval dt, in time interval dt. Number 3, Kepler's third law. Number 3, Kepler's third law. Elliptical orbit of revolution of planet around sun. Sun exists at one of its focus. Vector r is the distance vector of planet of mass m, small m. Small m is the mass of planet and capital M is mass of sun. Planet revolves around sun with orbital velocity v0. At t equals 0, the planet starts to move. And after one revolution, time will be t equals capital T, where capital T is the time period of revolution of planet around sun. The square of the time period of revolution of a planet around sun, the square of time period of revolution of a planet around sun is directly proportional to the cube of distance of planet from sun. Therefore, t square proportional r cube. T square proportional r cube.